Hi everyone, my name is Ryan Booz. I'm a developer advocate here at Timescale. We are starting a new series called Timescale Tuesday, and we hope that every week we'll post either a video, maybe a Twitter thread, a blog post, really trying to dig more into some usability of Timescale, APIs, ways that people are using Timescale, or maybe some questions they've had about how to use a particular function or the best way to approach a problem. And so for this one, I wanted to kind of take the spirit of the day. I am actually doing this recording on February 2nd in 2021. So in America, that is Groundhog's Day, made popular by a movie in the 90s, I believe it was, called Groundhog's Day, where Bill Murray plays this character, Phil Connors, and he relives the day. He goes to Punxsutawney, and he relives this day over and over again. And every morning he wakes up, and at 6 o'clock, the radio's playing Sonny and Cher. I hope it's playing in the background. And he has to live this day. Now, the cool part about it is really that he takes the opportunity to learn and try and improve himself. And so in the spirit of Groundhog's Day, I wanted to actually try and improve upon something I showed you last week. Now, I do want to say that here we are in 2020, in 2021, February 2nd. And so I actually live about 2 hours from Punxsutawney. I'm in Pennsylvania in the United States. And so the groundhog came out this morning and actually forecasted 6 more weeks of winter. I think this is a picture from this morning, which I fully believe because I am actually looking out my window and there's 18 inches of snow on the ground. We have just had a blizzard come through, so it's been quite a couple days. Man, I wish that groundhog was wrong. I hope he is. So I wanted to improve upon something I did last week. I took this last week and I've learned a lot about how I was using the stored procedures to solve a problem. So super quick recap. I had 100,000 computers, 1 million data points a minute. That equaled over 1 billion metrics per week. And I only had a 1 terabyte disk on a single Timescale instance. And so I wanted to improve upon that. There was no way for me to get more than a couple weeks of data onto that single node instance with 1 terabyte of disk unless I could use compression. But now I wanted to do this on a multi-node instance. So I showed you last week how to use the stored procedure and use what we call user-defined functions. So I added a job. I had a stored procedure I wrote that would go and find the oldest chunk once I had more than one chunk that was uncompressed. And it would just keep checking for chunks. And if there were chunks to compress, it would do it, but it would make sure the most recent chunk was left uncompressed so that I could keep importing data. But then I wanted to go ahead and do that same thing on a multi-node instance. And so you'll see in my Forge account, I have an access node and 4 data nodes. So there are my 5 instances, and they make up a multi-node cluster. So a 4 data node cluster. And I currently have almost the exact same data in there. I actually still have to go back into September and import a few weeks of data. And you can hopefully tell, I know it's a little bit small, but each of these has about 100 gigabytes of data compressed on it. It's the same thing. I have the most recent 2 weeks are left uncompressed, and the everything else is compressed. And so you can see that pretty quickly I'm not utilizing the data nodes as much, which is the beauty and the value of the data nodes. Well, I ran into one problem when I was doing this, and so that's why I thought I would show you how I improved the stored procedure. So this is the single instance stored procedure. You can see in the bottom left-hand corner, I queried how many chunks are compressed and uncompressed. That simply comes out of the Timescale information views that we have, the chunks view. It has a field, a Boolean called is compressed. With multi-node, we don't actually fill that value in. It returns as null. So if I run the same query on a multi-node instance, you'll see that I end up with 1,500 chunks, but nothing is coming back as compressed or uncompressed. The reason for that is honestly performance. In a multi-node cluster, number one, we don't really know how many nodes you have. And that view is a view for all chunks, whether or not the table is a hypertable or a distributed hypertable. For a distributed hypertable, because we can manage the data node, but currently there's still nothing stopping a user from actually connecting to the data nodes individually and doing work there. We're still deciding how best to always make sure the values we have within the views are synced appropriately. And so we don't keep track on the access node just in case something has changed. And we also don't want to go query all the data nodes every time you invoke that view, because there is a performance hit to distribute those nodes. Now it's often small, but we want it to be as fast as possible. Instead, we give you a function called compress chunk compression stats, which actually then you name the hypertable you want us to examine. It can be a regular or distributed hypertable. And if it's distributed, then we'll go out to the hypertable and ask for both the current status of each of the chunks and all of their statistics, the compression before and after and so forth. So I had to update my store procedure. So you may recall, if you go back and watch that video, I honestly pulled something together pretty quickly just to serve my use case, which again was I'm ingesting lots and lots of data in time series order. I just wanted to make sure the most recent chunk was left uncompressed. So if I had, in that case, more than one chunk, I could compress anything that was greater than the most recent one. In the case of a distributed hypertable, I need to make sure that I have an uncompressed chunk of the current time range on each data node. So I needed to improve the store procedure a little bit more. So I did a couple things to actually make this more reusable, both for a regular hypertable or distributed hypertable. So again, we allow you to pass in a configuration object. It's just a JSONB object. It's free form, whatever configuration you need to pass in. And so I created a couple new variables, which you'll see here. The ones I pass in are the hypertable, the range or the interval in which I want to look back in time to see if I have uncompressed chunks I can compress, and then how many chunks I can skip. So on a single node instance, I just need to make sure I have one chunk that is uncompressed. On a multi-node instance, I want to make sure I have at least one chunk per data node. And so in this case, it's 4. As long as I order the query correctly, the most recent, as long as I have more than 4, then I know that there are chunks on some of the data nodes that can be compressed. So I need to skip at least 4. Then whenever this function is invoked, it passes in that configuration function, the configuration value, that JSONB object. And we just simply use functions within Postgres to select out the values from each of those, each of the values in that JSONB object. And then, good programming would say we need to be defensive, right? So this is just an example of some ways we can do that. In this case, I've now made the hypertable a configuration option. So you have to set the hypertable that you want to compress. And I'll tell you why in a second. If you don't set it though, the function's not going to work. The store procedure will fail. And so I just raise an exception and stop it ahead of time. We also then, again, in my case, I wanted to set some default values if something was not passed in, how many chunks to skip, the interval to look back, and so forth. And then I'm doing some notices purely for my own benefit as this runs. And then we start the loop. And again, I showed this before. We're going to loop until there are all the chunks we want to be compressed are compressed, and then the store procedure will stop. And then the user-defined actions mechanisms will start it up again at the specified interval. In this case, it was 10 minutes later. So once the store procedure stops, we'll wait 10 minutes, and then we'll start it up again and see if there's any more chunks that we can compress. If there are, we do it. If there's not, we're done. And so the specific function is not, the query is not that much different. We are just looking to see if there are more than 4 chunks in this case. Remember, I have skip chunks. This variable right here is something I'm passing in. So if there are more than 4 chunks in this case on my multi-node instance, then we will find the one that is oldest, greater than 4 and oldest. And so in that case, I did add an order by. So we want to make sure that I'm grabbing the chunks that are oldest in time and leaving the most recent ones apart. Now in this case, if you're looking at this and you're really paying attention, you may realize that I don't care which data node it's coming from. Since I'm only doing one chunk at a time, technically we could do more than one chunk at a time. If I wanted to rewrite this even further, if this was a multi-node instance, I could maybe have 2 different variations here. And I could actually select a chunk from each data node And then in this perform, I could actually call that function compressed chunk 4 times. It would actually farm that out to each data node. And so I'd get really 4x the compression speed, right? Because I'd be compressing 4 chunks at a time rather than 1. I didn't choose to do that. It would take a little bit more work. And again, this served my need. I could continue to insert data, chunks would be compressed on the data nodes, and I would finish up. The only difference then, again, from the previous one is we have our add job function, which now says name the store procedure that we're going to call. And I've just added that additional configuration. All right, so that configuration now has skip chunks and hypertable. The cool thing about this, I hope that you see, is this, right? By adding something like this to the store procedure, we now have a store procedure or a job that could be called across any number of hypertables, distributed or non-distributed, right? So I can now use this exact same function. Let's say I had 2 hypertables. One is distributed. In this case, it's called CPU. And maybe I have another one called orders, right? So it's transactions of orders coming in through my system. Maybe CPU gets so much data, I want this store procedure to run every 10 minutes. But orders, I could let that hypertable maybe only be compressed once a day. You know, maybe I have 2 or 3 chunks a day, and I just want them to be compressed at the end of the day. So, you know, I want more control than maybe the policy allows. Well, I could use this exact same store procedure, add 2 different jobs, and just change the configuration options, right? So now maybe the range would be, you know, today, if it's a single node hypertable, maybe it would just be 1 chunk I'm skipping, or 2 chunks, it's up to you. But then I can name different table names, and I don't have to have different store procedures. So that is some of the value that I hope that you can start to see with this mechanism in user-defined functions. It solved my specific use case. It doesn't mean this is exactly the use case you have, but hopefully it starts to get you thinking again in ways that this can be possible. And now you can see the compression, how you could do compression on a distributed hypertable currently in TimescaleDB 2.0. So I always want to mention this. If you're not part of the conversation with us, please come join our Slack channel, slack.timescale.com. It's a great place to come find out what we're doing, figure out announcements, see what people are talking about. A lot of stuff happens there. Thanks so much for watching. I hope that these first 2 videos dealing with user-defined actions and compression start to help you understand Timescale just a little bit better.